Hello students, welcome back to my YouTube channel Physics Club by Shakti sir. So in today's lecture we will discuss about the collision, particularly the elastic collision in one dimension. So let's start with the concept. So we will use the two type of concepts in this topic. First is the conservation of linear momentum, you know that, which is based on the Newton's second law. That is, when the net external force acting on the system is zero, then the linear momentum of the system will remain conserved. So in this situation, we are considering the isolated system. So let's consider this is the isolated system, and in this system we have two objects. One is mass m and the other one is mass 2. Both are moving with some velocities. Let's say the m1 mass is moving with velocity u1 and m2 mass is moving with velocity u2. So the linear momentum of m1 will be m1 u1 and the linear momentum of m2 body will be m2 u2. As there is no external forces acting on this system because it is the isolated system we are considered, so the total linear momentum of this isolated system will remain conserved. That is, the total linear momentum of this isolated system before the collision can be written as m1 u1 plus m2 u2, like this. Clear? Okay. The second thing is we will do the conservation of linear momentum as a concept to solve the numerical in this collision. So what we can write like this: the total linear momentum of the system before collision can be equals to the total linear momentum of the system during collision, and that can be equals to the total linear momentum of the system after collision. So this is one of the fundamental equations we will get to solve the numericals based on collision, that is the conservation of linear momentum, which is valid in any type of collision, either elastic collision or inelastic collision. Okay, so let's say after the collision we have the situation something like this. After the collision, the m1 body is moving with the velocity of v1 and m2 body is moving with the velocity of v2, and we are considering the right direction as the positive direction. Okay, so the final momentum after collision can be written as m1 v1 plus m2 v2, like this, right? And based on the conservation of linear momentum, we can easily equate the linear momentum of the system before collision is equals to the linear momentum of the collision after collision. So this is our before collision equation and this is our after collision equation. So we can equate these two. This is the equation we will get to solve the numerical. m1 u1 plus m2 u2 is equals to m1 v1 plus m2 v2, right? So this is the one equation. So it means we can only solve the one variable from this equation. We can use the energy conservation equation also to solve the numericals, and here we can say there is a very important role of the kinetic energy conservation. But keep in mind, the kinetic energy conservation is only conserved in elastic collisions, and particularly for the collisions when we have a situation before the collision and after the collision. That is, the kinetic energy of the system before the collision is equals to the kinetic energy of the system after the collision, not during the collision. Like we have the situation here, the linear momentum is conserved even during the collision, but the kinetic energy is not conserved during the collision. And there is a very much valid reason why it is not conserved during the collision, because when the, when the two balls are colliding with each other, for example, you have two balloons and you just press the two balloons together, you will observe that the shape of the balloon changes, right? The shape of, even if you have two tennis balls and you collide the tennis ball and bat, anything, or ball and wall, so what you will see, the shape of the tennis ball change, and during that change the kinetic energy before the collision is converted into some form of deformation potential energy, because there is a deformation in the shape of the ball. So some potential energy is stored in that situation when the ball is deformed. So initially, let's say you have a kinetic energy of 100 joule, but during the deformation, let's say 20 joule is converted into the deformation potential energy, And in this situation, that is during the collision, you have 80 joules of kinetic energy and 20 joules of deformation potential energy. That's why we cannot conserve the kinetic energy equation before the collision and during the collision, because they are not equal, right? But once the bodies rebound, because these are elastic collisions, so definitely the bodies will rebound after the collision, and after rebounding, what will happen? After rebouncing, what will happen? They will acquire their initial shape. The ball will acquire their initial shape. The body will acquire their initial shape. That is, whatever the deformation energy will convert it back into the initial kinetic energy. That's why I'm saying the initial kinetic energy and the final kinetic energy, that is before the collision and after the collision, is conserved, but not during the collision. And the very valid reason is why? Because due to the formation of deformation potential energy. Okay, so we can easily write the equation like this equation. This is the equation in form of kinetic energies. So this is the kinetic energy before collision of the two bodies, and this is the kinetic energy after collision of two bodies, right? And based on these two equations, that is the conservation of linear momentum and the conservation of kinetic energy, based on these two equations, we can solve v1 and v2 variables, that is the velocities of the body after collision. So according to my assumption that in your classroom you have solved this, your teacher has given you the detailed derivation how you can solve the value of v1 and v2. So I'm not going to discuss this, but what here is important, that what are the final results and how we can use those final results to solve the numericals. So here the final results, we get the v1, which you need to remember if you are preparing for the entrance exam. So v1 will be equals to m1 minus m2 divided by the total mass of the system, u1 plus 2 m2 u2 divided by total mass of the system. So how I remember this? I write 1 1 1. This is the pattern. 2 2 2. This is the pattern. So this is how I remember, like what to write first, m1 or m2. If this is v1, that is 1, then 1 1. If this is v2, 2 2 2. So once you are done with one terms, then you have 2 2. And once you are done with two terms, then you have 1 1. Okay, so this is the my practice. If you write this equation near about 10 times, you will remember these equations. Okay, further that we have a special case, that is when the bodies which are colliding have the same masses, that is the two bodies which are colliding have the same masses, then what will happen? The very straightforward answer is they will just exchange their velocities. Let's say if the one body is at rest and the other ball collide with the ball at rest, then what will happen? The ball which is moving initially will stop, and the ball which was at rest get motion, get velocity, the same velocity of the first ball, because they just exchange their velocities, right? So as it is shown in here, that is before the collision, let's say we have two bodies m1 and m2, A and B. So body A has a velocity of 4 meter per second, body B has a velocity of 3 meter per second. This is the situation before the collision. And after the collision, you will see that they just exchange their velocities. That is, body A gain the velocity of B. You can see this is the velocity of body A after the collision, and this is the velocity of body B after the collision. So initially body A has 4 meter per second, but after the collision body B has 4 meter per second. Even their directions remain same. You can see 3 meter is moving towards left, so 3 meter per second moving towards left. So this is how the very straightforward answer is. When the masses of the body in elastic collision, when they collide, what will happen? They just exchange their velocities. Another important point here need to discuss is there are the situations when one body has a very large mass as compared to the other body. Under this situation, let's say m1 is much greater as compared to m2, so we can write m2 divided by m1 approximately equals to 0. So this type of situation, when we put equals to 0, we will get our relevant answers. Let's solve some numericals. So our numerical number first is two balls of masses m and 2m are moving in opposite direction. So let me draw the two balls of masses. Let's say this is m and this is 2m are moving in the opposite direction. Collide head-on elastically with velocities v. So this is velocity v and this is velocity 2v. Find their velocities after collision. So what we need to here, this is our u1 and this is our u2. So in vector form, if you write u1, what will be the answer? It is v, because it is toward right. But u2, the direction of u2 is towards left, so you will write negative of 2v, this term. Okay, now we will use these equations to get the answer v1 and v2. So let's write values v1. So v1 will be v1 velocity is equals to, so m minus m2 divided by total mass m1 plus m2, right? Here u1 vector plus 2 times of m2 u2 divided by m1 plus m2. Let me put the values and let's see what will be the answer. So m1, this is our m1 and this is our m2. Okay, so m1 is equal to m and m2 is equal to 2 times of m. Total mass of the system is 3m and the value of u1 is v. Okay, positive v. m2 is equal to 2m divided by 3m and the value of u2 is negative of 2v. This is u2. Okay, so let's solve this equation. So v1 vector is equals to negative m divided by 3m v. The negative, it is 4 to the 8 divided by 3, m cancel, v. So m cancel. So what you will get as a v1. So v1 here you will get negative of 3v. Okay, so this is the value you will get after solving this term. So this is our v1. Now we will write the equation for v2. So v2 is equal to, let's solve it. It is m2 minus m1 divided by m1 plus m2, like this, and then here you will write u2 vector plus 2 times of m1 u1 vector divided by m1 plus m2. Let's put the values. m2, what's the value of m2? It is 2m minus m divided by 3m, and u2 is equal to, it is negative 2v plus 2 times of m1 is equal to m divided by 3m, and u1 is v. Okay, let me solve this. So it is 2m minus m is m divided by 3m. This is negative 2v, and here m cancel. You will get 2 by 3v. Here again m cancel. So it is negative 2 by 3v plus 2 by 3v. So what can be the answer? So you will get 0. So your v2 is 0. So these are the velocities of the two bodies after collision. v1 is equal to negative 3v and v2 is equal to 0. Okay, easy. Just put the values in the formula. Question number second. Question number second is here. We have two blocks A and B. Block A is, you can see block A is at rest, but a spring is attached with the block A having spring constant 200 Newton by meter, and block B is moving with the velocity of 2 meter per second. What they are saying, block B collide with block A with a velocity of 2 meter per second. Find the maximum compression of the spring. So when this block collide with this spring, what is the maximum compression in the spring? So there we will learn a new concept in this situation. So let's solve the situation. Okay, so first concept here we will use, that is the conservation of linear momentum. So what is the linear momentum before collision? So that is the linear momentum before collision is equals to mass into velocity, that is u1, and you can simply write is you can see the mass is 1 kg, right? So what you'll write, mass is equal to 1 and it is 2 meter per second, and for other body the velocity is 0, that is the block A having velocity 0 initially. So the total linear momentum here is simple, 2 kg meter per second. This is the total linear momentum of the system before collision. Now during the collision, what will happen? This is the concept you need to know. During the collision, at the maximum compression, what will happen? Both the blocks will move with the same velocity. At the maximum compression, always remember this line, at the maximum compression, what will happen? Both the blocks will move with the same velocity. So this is the concept you need to remember. At the maximum compression of the spring, both the blocks will move with the same velocity. Okay, so let me highlight this. This is the concept and we need to remember these lines. These are very important. All right, now at the maximum compression, the situation is something like this. Let's say this is our block B, here is the spring, and this is our block A. Both are moving with the common velocity, let's say Vc, common velocity, right? Their masses are equal, 1 kg. So what is the linear momentum in this situation? So the linear momentum here during the collision is equal to mass into velocity Vc plus mass into velocity Vc. So you will get 2 times of Vc. This is the situation during the collision. Now we will conserve our momentum, that is before the collision and during the collision. What you will get? So by conservation, so conservation of momentum, by the conservation of momentum we can write it as before the collision is 2 kg meter per second, and after the collision you will see 2 Vc vector, like this, right? So 2 cancel, right? 2 cancel. So 2 is for mass. What you will see here, you will get it is 1 meter per second is equal to Vc, because the unit of velocity is meter per second. This is the common velocity with which both the blocks are moving during the collision. Now, but we need to calculate the maximum compression. To calculate the maximum compression, what we need to do, we will apply one more equation, one more conservation law, that is the conservation of mechanical energy. So second concept we will use here. Second concept is conservation of mechanical energy. Conservation of mechanical energy. So in this concept we will conserve the energies before the collision and during the collision. Before the collision, the energy is total kinetic. So mechanical energy before collision is purely kinetic energy, and mechanical energy during the collision is kinetic plus due to the compression of the spring, there is a elastic potential energy stored in the spring. So we will write the equation. What is the equation? The equation will be kinetic energies before the collision, that is 1 by 2, mass is equal to 1 kg and speed is equal to 2 meter per second. For block A, the kinetic energy is 0 because it is at rest. And during the collision, both the blocks are moving and their kinetic energies are same because they have the same mass and same speeds, with common speed 1 meter per second. So 2 multiply 2 is for 2 blocks, and this is kinetic energy half, mass is equal to 1, and their common velocity is again 1. Okay, so this is the kinetic energy of the system during the collision, plus there is one more energy, that is the spring energy, right? How we can write it is half k x square. We need to calculate this x value. What's the value of k? So let's put the value of k. So this is half, k is equal to 200 and x square. When we solve this equation, what you will see, 2 cancel, so you will get 1. Here again 2 cancel, you will get 1, right? Plus 100 x square. This is what I, oh okay, wait, there is a mistake. So half mv square here. So half mv square means you will get 4 divided by 2 is 2. Here you will get 2. Okay, so 2 minus 1 is 1, equals to 100 x square. So 1 divided by 100 is equals to x square. So it is 0.0, or you can say, because this is square, so 1 by 10 equals x. So x equals to 0.1 meter. So this is the maximum compression in the spring. This is our answer. Okay, I hope you understand. We use two concepts, concept 1 and concept 2. So this is the conservation of mechanical energy. One concept is this one. All right, let's move to question number 3. So question number 3 says, two blocks of masses 3 kg and 6 kg are placed on the smooth horizontal surface. They are connected by a light spring of force constant 200. Initially the spring is unstretched. Keep in mind, unstretched. The initial velocities are imparted to the blocks. So these are the initial velocities, 1 meter per second and 2 meter per second. Find the maximum extension of the spring. In this case, they are asking to calculate the extension. Again, we need to calculate the value of x. So by the same method, we will apply the concepts conservation of linear momentum and conservation of mechanical energy. So let's start with the conservation of linear momentum. So initially, linear momentum, so P initial or before can be written as this is mass is equal to 3 kg, but the velocity is toward left, so negative 3 multiply 1 plus there is mass is 6 kg and the velocity is 2, so you will get 12 minus 3 is 9, okay, kg meter per second. This is the initial linear momentum of the system. All right, and at the maximum extension, you know that they will move with the common velocity. Again, we will use the concept. At the maximum extension, both the blocks will move with the common velocity. So what's the common velocity? We will calculate. So let's say Vc is the common velocity. So by conservation of linear momentum, by conservation of momentum, that is linear momentum before is equals to linear momentum during the collision. During the collision, they have the common velocity. So what we will write, before is 9 and during the collision there are two, this is mass times v common plus mass times vc, that is the common velocity. So 9 equals to 12 vc. Okay, so what you will get, 9 plus 3, sorry, this is a silly mistake, this is 9 VC. So 9 cancel, so VC, you will get VC is equal to 1, so 1 equals to VC, that is 1 meter per second. Okay, meter per second. So common velocity at the maximum extension is 1 meter per second. Now we will apply the conservation of mechanical energy. So apply conservation of mechanical energy. So initially you will see that the spring is unstretched. It means that it has only the kinetic energies. So the kinetic energies before the collision is half mass is equal to 3 kg and velocity plus half mass is equal to 6 kg and the velocity is 2, like this. And after it is half mass is equal to 3 kg and velocity is equal to 1, then half mass is equal to 6 kg and velocity is again 1. And spring energy, how we will write the spring energy? Half kx square, and the value of k is 200, so we will write simply x square. There is only one variable, we will calculate the variable as we solved it earlier. So you can solve this equation easily, and once you are done you will get the value x is equal to 0.3 meter. This is the value you will get once you solve this calculation. Okay, so this is our answer. So this is all about for the elastic collision in one dimension, particularly with the concept and 3 examples. I hope you will enjoy this lecture. In the next lecture we will continue this for the inelastic collision and the more varieties like the coefficient of restitution and the multiple collisions with the floor and all that stuff. Wish you all the best. Bye bye.